Okay, good morning. Welcome to
MathPractice153.
MathPractice number 153. Today we're going to talk about a little bit about summing squares and a little bit about math history. Okay?
Yep.
You excited?
Yeah.
All right, high five. Okay, so last week we talked in Beast Academy. We were doing things like this. We had a 3x3 square and we wanted to chop it up into smaller squares. Can you show me how you did that? Okay, awesome. So you made this 2x2 square, this 1x1, this 1x1, this 1x1, this 1x1. Okay, so this says there are 9 tiles, and this is 4 plus 1 plus 1 plus 1 plus 1 plus 1. 5 ones, right? 1, 2, 3, 4, 5. Or 3 squared equals 2 squared plus 1 squared plus 1 squared plus 1 squared plus 1 squared plus 1, 2, 3, 4, 1 squared. Okay, and now we're going to do it just not with the geometry. So today's Beast Academy is saying we're not going to do geometry, we're just going to do it with numbers. So we could say that 3 squared equals, a different way we could do this is 2 squared plus 2 squared plus 1 squared. So 4 plus 4 plus 1 equals?
Equals is 9.
9. But we can't do that this way. We can't interpret this geometrically. Because there's not 2x2. There's not two 2x2 squares inside of there, right?
Yep, there's equal mass.
There is equal mass, right?
Right here.
Yeah, we could fold that in or turn that into a 2x2 square. I mean, with like a pair of scissors.
Yeah.
But it's not there. But this is still pretty fun, and we did some examples already today of this. But what I wanted to talk about, it seemed like a nice thing to talk about, since last week when we were doing this stuff with the squares, we mentioned there's something called the Pythagorean Theorem for right triangles, where you have A, B, and C in a right triangle here, and we know that A squared plus B squared equals C squared, and we showed some examples like 3 squared plus 4 squared is 5 squared. You remember what 3 times 3 is?
9.
Remember what 4 times 4 is?
16.
Remember what 5 times 5 is?
25.
Do you remember what 9 plus 16 is?
25.
Good job. And there were some other examples like this too, like 8 squared plus 15 squared equals 17 squared, but we're not going to go into that right now. The one thing I wanted to tell you about is that this is very special with squares. Very special. If you try to find solutions for cubes, A cubed plus B cubed equals C cubed, there are no solutions to this. None. So if we thought, well, maybe 3, 4, and 5 work again. 3 cubed plus 4 cubed equals 5 cubed. Let's see. 3 times 3 is 9. Times 3 is?
Is 27.
27, good. 4 times 4 is 16, so that's 4 squared. 16 times 4 is?
64.
64, very good. 5 times 5 is 25. Times 5 is?
125.
125. Okay, now does 27 plus 64 equal 125?
No.
What does 27 plus 64 equal?
Well, it equals 20 plus 60, which is 80, and 7 plus 4, which is 11, so it's 91. 91 does not equal 125. But that, okay, so that's okay. So it turned out that people knew that there was no solution for the cubes, and then in the 1630s, long time ago. Yep.
They didn't even have iPhones then. Can you believe that?
Whoa.
Whoa. 1630s, someone named Fermat said that A to the n plus B to the n equals C to the n has no solutions for n greater than 2. So for a squared plus b squared equals c squared has solutions, but never bigger than 2. And then he said, I know how to prove this, but it's too big to write down. Sounds suspicious?
Yeah.
Yeah. It's like when you say, I don't have enough time to clean up my room. Right?
Yeah.
Yeah. Okay, so, but later on in the 1990s, someone at Princeton named Andrew Wiles did write down a proof. In the 1990s, that's a pretty long time ago, right?
Yeah.
They didn't have iPads then. Can you believe that?
Whoa.
Whoa. Andrew Wiles wrote down a proof, so I'm going to write it down for you. Oh, you know what? I don't have enough room to write it down. That sounds suspicious?
Yeah.
Yeah, well, he really did prove it. And I really don't have enough room to write it down.
Yeah.
Yeah, so, and he's at Princeton. He's a very famous mathematician at Princeton. So we have our Pythagorean triples, like 3, 4, and 5.
Yep.
Cubes don't work, fourth powers don't work, nothing ever works above that. Isn't that amazing? It's one of the most elegant problems in math. And one of the most famous ones too. It's called Fermat's last theorem. Alright, is that fun?
Yeah.
Alright, good job today, sweetie. Good job.